Well, we've looked at how rocket engines work to get rockets off the ground up into orbit. That's the power part of rocket science. But you need a lot more if you really want the rocket to go where you want it to go, and that gets us into the area of control theory. Sort of as a joke, we sometimes say that the first law of rocket guidance is pointy end up. And that's great, because that's the direction we want to go. But it actually gets a lot more complicated than that. Control theory is a rather complex field, and it gets into some pretty hairy mathematics, which we're not going to deal with here. And it's not limited to aerospace engineering. I mean, control theory applies to electronics, to mechanical engineering, to controlling all sorts of vehicles and different systems. In fact, most of us have had experience with control theory. If you're riding a bicycle or driving a car, I mean, we look out the window when we're driving a car. If we see that the car is going just a little bit to the right, what do? We move the steering wheel to the left. That's a control system. The elements of the control system are sensors and actuators, and of course the whole system which we're trying to control. And in the case of driving a car, your sensors are basically your eyes, that's telling you which direction you're going, and the actuator is the steering wheel, which is connected to the wheels of the car. And in general, the corrections that you have to make are slow enough that our brains can keep track and that the car is capable of following the commands that we give it. Of course, for rockets, it gets a lot more complicated. You need accelerometers to tell you how fast you're going. You need gyroscopes to tell you the direction you're going, and all those have to be integrated. And then you have the control system, which effectively controls the direction that you're going to move. As an example, we have a sequence here of about 3.5 minutes before the launch of a space shuttle. The actuators for the shuttle are twofold. First of all, we have aerodynamic actuators on the elevons and the tail rudder, which control the vehicle when it's in atmospheric flight. And then we have the rocket engines themselves, which control the direction during launch. And all of these are controlled by a very powerful hydraulic system. And before we actually commit to launch, we want to check to make sure that the hydraulics are working okay. So about 3.5 minutes before launch, the hydraulic system has been turned on, and we actually use it to move the actuators, which we're going to take a look at now in a close-up. So take a look at the rudder here, and there you go. You can see it moving back and forth. That's what we call the actuator of the system. And now take a look at the 3 engine bells, and they will move back and forth. Here they go. And if you have to control the direction of the rocket, that's what we use that motion of the engine bells for. Everything is working okay here, and so we're ready to commit for launch. Of course, sometimes things don't go quite as you plan. Either the sensors have a problem or the actuators don't work properly, and the results can be quite dramatic, as we'll see in this video of the launch of a Russian Proton rocket. And we have liftoff. Everything looks okay at the beginning. Uh-oh. Things are not going as planned. Pointy end up, please. Nope, this isn't going to make it. Well, that's what happens when the guidance system goes wrong. And, well, here the whole system has been destroyed by the ground safety officer. I'm actually not an expert in control theory, and fortunately, in MIT's Department of Aeronautics and Astronautics, we have quite a few experts, among which is Professor John Howe, who is the head of our Aerospace Control Lab. He's an expert in the guidance, navigation, and control of autonomous vehicles, and he's done some really amazing stuff with quad-rotor copters and with driverless cars. And he's going to talk to us now about an introduction to control theory, done on a level where you don't need heavy-duty mathematics to understand it. So I'll turn it over to Professor Howe, and let's learn something about control theory.